Let's look at OpenStax College Physics, Chapter 14, Problem 24. A 0.05 kilogram ice cube at negative 30 degrees Celsius is placed in 0.4 kilograms of 35 degrees Celsius water in a very well-insulated container. What is the final temperature? All right, let's write down the knowns and unknowns. So we have a mass of ice of 0.0500 kilograms, and the initial temperature of ice is negative 30.0 degrees Celsius, and that is mixed with mass of water is 0.4 kilograms, and the initial temperature of water is 35.0 degrees Celsius. The two of them are mixed, and they will reach some final temperature, and that's what we're looking for. So here I have a diagram in which on this axis there's a temperature in degrees Celsius, and on this axis I have time. I could have also used energy, and we have a system that is made up of ice and water. What we know is that the ice is going to heat up and the water is going to cool down. So I'm going to draw those processes on my diagram. So I'm starting with ice at negative 30 degrees Celsius and with water at positive 35 degrees Celsius. So I know that the ice will heat up to 0. At 0, it will start melting, so it will stay at 0 until all of the ice has melted, and after that it will heat up to some final temperature. All of this happened because the water released some heat, and we're going to have here an equilibrium, and this is the equilibrium temperature. So again, the water released heat, and that heat was sufficient to warm up the ice from negative 30 degrees to 0, then to melt the ice, and then to heat up the water that used to be ice to a final temperature. Then we'll say that this is Q released and this is Q absorbed. So the water is the thing that releases the heat, the ice is the thing that absorbs the heat. We can't quite say that Q released equals Q absorbed because by convention, heat that's released is a negative quantity, heat that's absorbed is a positive quantity. So I can't say that a negative quantity equals a positive quantity, which is why we will take Q released in absolute value so that we have a positive quantity equal a positive quantity. Now, I like to write on these lines what they represent. So I know that water cools down from 35 degrees Celsius. So here I have the heat released is mass of water, specific heat of water, times, I'm going to take the higher temperature minus the lower temperature so that I have a positive quantity here, an absolute value of Q released. And that's going to be T initial water minus T final. Then I have the ice that is warming up from negative 30 degrees. So that would be mass of ice times the specific heat of ice times T final, which is 0, minus T initial ice. Then on this, at 0 degrees Celsius, we have a phase change. So we have to use mass of ice times the latent heat of fusion of water. And then once all of the ice became water, we have mass, it's still the same mass of ice, times specific heat, but now it's the specific heat of water. So here, I use the specific heat of ice because it was still in ice phase, but here we're having to use specific heat of water because now it's water. And then we have T final minus 0. All right, so I'm going to write all of this down as an equation. So starting out with absolute value of Q released equals Q absorbed. Then I have mass of water, specific heat of water times T initial water minus T final. so that's the absolute value of Q released, is equal to mass of ice, specific heat of ice, times 0 minus T initial ice. Then to that I have to add the latent heat of fusion, so that's mass of ice, latent heat of fusion. And to that I have to add the last bit here, mass of ice, specific heat of water, times T final minus 0. I'm going to skip the 0. All right, so I have to solve for T final. So T final will be mass of water, specific heat of water, T initial water, plus mass of ice, specific heat of ice, T initial ice, minus mass of ice, latent heat of fusion, divided by mass of water plus mass of ice times specific heat of water. Double check the calculation. So I'm going to skip units here. Mass of water is 0.4 and sig figs because I'm going to have a really long equation. So it's 0.4. Specific heat of water is 4186. And the initial temperature of the water was 35 degrees. Then I have mass of ice that was 0.05. Specific heat of ice is 2090. That's from a table in the textbook. And T initial ice was negative 30 degrees. Then minus mass of ice 0.05. Latent heat of fusion for water is, again from a table in the book, 33.5 times 10 to the 4th. And we divide this by the mass of water plus mass of ice, so that is 0.4 plus 0.05, and multiply it by specific heat of water, 4186. And when we plug these numbers into our calculators, we end up with a final temperature of 20.6 degrees Celsius. Now, I kind of lucked out in this problem. I wasn't aware whether the amount of heat that was released by the water would be sufficient for the ice cube to go through all of these processes. I just assumed that this is what would happen. Let's say that we would have obtained value that was negative here. That would have meant that there wasn't enough heat released by the water to melt the ice cube. So then we would have had to actually just calculate the amount of heat released by the water, compare that with the amount of heat needed for the ice to melt, to see that, the ice didn't melt, or the final temperature would have, then possibly this water would have cooled off more. So these are things that you'll have to juggle with in a problem if it's as vague as this problem here. You don't know exactly if the final temperature is going to be positive or negative.